Hi, folks. My name is John O'Reilly. I'm based in Galway in the west of Ireland. I work remotely for a company called Neat up in Oslo. And it's a pleasure to be back in Berlin talking to you today. A very small bit about myself. I'm a Kotlin GDE. I've been working as a software engineer for over 30 years now. And I've been working in the Android iOS ecosystem since around 2009. So as the title suggests, we're going to talk today about a couple of key areas that I feel have contributed to the increasing convergence of native iOS and Android development. An emphasis on native here, by the way. First up, we'll cover some examples of how similar the Swift and Kotlin languages are. This isn't necessarily something new, but is, of course, an important element to this dynamic. But as useful as that is, what I think is more impactful is the very similar approaches we now have on iOS and Android to both UI development using Jetpack Compose and SwiftUI. And also, more recently, the fact that we now have much the same mechanisms available for managing concurrency on both platforms. And just to also mention, somewhat in the context of both platforms using declared UI frameworks, is I think we've converged to a large degree on the use of MVVM, or at least a unidirectional data flow variation of it. And we'll see a small example of that later. Lastly, not something I'm going to talk about in any detail, but also interesting, I think, to note how similar Android and iOS devices have become and the closer alignment of UX patterns. Just wanted to show at this point some of the key milestones that brought us to where we are today. Both platforms started growing in earnest around 2008, 2009. And of course, at that point, and for a while after, we were developing apps using Java on Android and Objective-C on iOS. And these, by the way, were some of the devices we had at the time. This is an iPhone 3G and the funky G1 device. So needless to say, devices have changed a lot since then, and as I said, become a lot more aligned. Fast forward then to 2014, Swift is now supported on iOS, and 3 years later, Kotlin on Android. Languages, as we've mentioned, that are significantly more similar to each other than Java is to Objective-C. 2019 then was a key year for UI development on both platforms. Jetpack Compose was announced at Google I/O that year and formally released in 2021. SwiftUI then was announced at WWDC that year and released later the year. And lastly, we saw the announcement of the new Swift 5.5 concurrency functionality at WWDC 21. So just some brief additional background context to some of these developments before we dive into the comparisons. This was an article written in April 2019 by Jesse Wilson from Square, talking even at that point about how Android and iOS development was converging. He was primarily basing this on similarities in the languages, device and UX alignment, like I mentioned, and also mobile team organization. But within 2 months of that article, we'd see announcements of frameworks on both platforms that would have an even bigger impact on that convergence. First off, a few weeks later, we saw the announcement of Jetpack Compose at Google I/O. Then about a month after that, SwiftUI was announced at WWDC. And in terms of my own interest in this area, I had that time, as part of the Kotlin multi-platform work I was doing, been developing a native iOS application. And as someone that hadn't really been opening up Xcode that frequently for a while, I always struggled, again, to remember how to set up storyboards, view controllers, table views, and so forth. I'd seen the announcement of Jetpack Compose at Google I/O, but to be honest, it was still a little abstract to me at that stage. I didn't really appreciate at that point what declarative UI was all about and the impact it would have on mobile development. I watched WWDC then, saw the announcement of SwiftUI. It was available in Xcode beta that evening, and in the early hours of the morning, I had my first basic SwiftUI app. And I finally appreciated what declarative UI offered and how intuitive it made UI development. Something down the road that would be many people's experience in using Compose on Android for the first time. By the way, one interesting point worth noting here as well is I think the different sequence in which some of these capabilities became available on each platform. On iOS, we started with declarative UI and later added structured concurrency, and whereas it was the other way around for Android. And I think this has some implications, as we'll see, maybe for how existing functionality has had to evolve on both platforms. Okay, so let's dive into some of the comparisons. Firstly, the languages themselves. So I'm not going to do an exhaustive comparison of Kotlin and Swift. Rather, I'm going to use a number of examples to illustrate how they compare. A lot of the side project I do tends to be sort of Twitter-driven, so I'm going to be mostly using examples from various Swift iOS articles like this that I've seen people in the community tweet about. So John Sandell wrote this article recently on different ways of iterating over a Swift collection, and I thought it would be interesting to see what the Kotlin equivalent would be. So if we look at the first few examples from the article, probably won't take people too long, but at a glance, can folks spot which is Swift and which is Kotlin? Any takers? Yeah, and if we add in the array declaration, it's a little clearer which is which. Differences in use of parentheses, let versus val, print versus println, for example, but clearly very similar other than that. A few more from that article, and again, key thing here is how, at a minimum, Swift is at least very readable to someone that knows Kotlin and vice versa. And probably wouldn't take a developer from either platform that long to figure out how to write code for the other. And lastly, from John's article, we see some examples of iterating over maps. And again, I think we see even more closer similarities here again, map declaration, variable aside. OK, lastly in this section, another recent article, this time from Sarun, talking about sorting Swift arrays. And again, we see the similarities. API is almost identical in initial two examples, a few differences in how we set up custom comparators, but again, easy to understand either approach. And by the way, we'll see some additional examples in the language in the next few sections where we talk about declarative UI and structured concurrency. Also, just kind of added in this note after watching Kevin's talk earlier, it's important to mention this point, as Kevin touched on, that the languages are similar, and of course they have differences. And they have differences in important ways. I don't want to imply in any way that they're identical, but in the context of this talk and in the context of sort of what I'm discussing here, I think the similarities are still very important. OK, we're getting to comparisons of what I think are the more impactful similarities we have today. Finally, firstly, the use now of declarative UI frameworks on both platforms, SwiftUI on iOS and Compose on Android. Most folks here are probably somewhat familiar with Compose, but just to level set somewhat. So a common way of explaining declarative UI is the what versus the how. With declarative UI, we declare what our UI should look like in a particular state. And state is very important in this context. Any changes in state cause the appropriate parts of our UI to be re-rendered or recomposed. Another interesting implication of this approach, then, is that it at least encourages use of MVVM on both platforms. And it typically, as mentioned, unidirectional data flow variation of it. As well as SwiftUI and Compose, it's also the approach used in the likes of React and Flutter. And as we mentioned earlier, SwiftUI was released in 2019 and Compose in 2021. So this was a tweet from Thomas Rickward about a GraphQL sample he created using the Apollo library. I'd been using Apollo in shared Kotlin multi-platform code, so I thought it would be interesting, with Thomas's blessing, to create a Compose and SwiftUI version of the project that consumed that shared code and used the multi-platform version of the Apollo library. These are iOS, Android screenshots from the sample, and we're going to drill down and compare, for example, how a row in the list would be represented in SwiftUI and Compose. So at a glance, we firstly see that SwiftUI uses structs to represent UI elements like this, whereas Compose uses Kotlin functions. But if we ignore what you might call the outer wrapping around the UI elements, I think we see more clearly how similar these are. Some differences, of course, like hstack, vstack in SwiftUI versus row column in Compose. We have an async image in both SwiftUI and Compose to display an image from a URL. There's text elements in both, with some differences then on how styles are applied. But again, the key thing here is how closely the concepts align and how easy it's becoming for developers to sort of translate the UI from one platform to the other. And hearing more and more cases where this is happening, UI might be originally done in SwiftUI, and then a Compose version is done based on that, and vice versa. Another example from one of the samples I have, this time illustrating use of Canvas on both SwiftUI and Compose. This particular sample is perhaps a little bit obscure. It makes use of what's called a chip8 emulator in shared Kotlin multi-platform code. This was an instruction set used in the arcade games of the past, for example, like Space Invaders. It has the concept of virtual CPU and virtual display, for example. So what we want to display is generated as an array of data from the chip8 emulator code as it runs its program, and we need to show that then in SwiftUI and Compose. So we're able to use, as I said, Canvas in both SwiftUI and Compose, with, again, very similar code used for both. Here, we're iterating over that virtual display data. We're getting from the emulator as it runs its program, and then using Canvas on APIs on both to update the UI. Again, small differences in the APIs used, but again, fundamentally the same approach. And one more example from another sample I have, this time for this Fantasy Premier League app, again using SwiftUI and Compose. Again, we see the similarities in structure here, and in particular, if we focus in on the UI elements. Some differences, again, in the APIs used, and how styles, padding, etc. are managed, but much the same other than that. In general, if we think of our UI as a tree of components, then what we typically see is closer similarities to ones like for ones like this, but perhaps some bigger differences as when we move to, say, screen-level representation in terms of how, for example, navigation is managed, but still conceptually the same approach being used. And speaking of navigation, there were some changes announced at WWDC recently that make the approaches to navigation at least somewhat more aligned than before. This is a pared-down example from Compose code in the People in Space sample, showing some of the key moving parts of how navigation could be managed using nav host and composable then for each destination. And this is what this might look like in SwiftUI now with iOS 16 updates, using navigation stack, navigation destination, which map somewhat loosely to Compose's nav host composable. Some differences in that Compose uses route-based approach, where SwiftUI maps to destinations using data type, example, the assignment class here. Different handling of start default destinations, but at least with these updates, I think the approaches are certainly more closely aligned than they were before. One more SwiftUI announcement from WWDC this year, this one in relation to applying text styles across a group of controls. Relatively small change, but again, one that allows that bit closer alignment between SwiftUI and Compose. In this example, we're applying bold text style to all elements within the VStack in SwiftUI and column in Compose, using provide text style in Compose to achieve the same purpose as that font weight in SwiftUI. Semantics, again, a little different, but the same concepts being applied in both cases. Worth noting also that we can now use declarative UI frameworks for watch devices on both Android and iOS. Yuri contributed this Compose for Wear example to the People in Space sample. Hopefully, folks got a chance to see his talk earlier today. And on right, we see the watchOS version based on the SwiftUI, also contributed to the People in Space project. And again, sort of similarities in the approaches being used. Lastly, in this section, I thought it would be interesting to point out that not only do we now have support for widgets on both platforms, but we can again use the same declarative UI approach for developing them. And also, again, just FYI that Marcel will be talking about the Glance API this afternoon. I think he's on the next session after this. Next up, concurrency. And more specifically, we're talking about the structured concurrency functionality that we now have on both platforms. This is a really powerful capability that allows us to write async code in a way that's easy to read, and also allows a more deterministic structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended at particular points and resumed later. And as we'll see in a moment, Swift supports this through things like tasks, async functions, and async sequence, and Kotlin similarly through coroutine, suspend functions, and flow. This approach, for example, allows async functions to execute sequentially and in parallel. I'm going to show examples of both shortly, along with some examples of how to use async sequence and flow. And a very important aspect of this is how invocation of code like this can be tied into the UI lifecycle, thus allowing, for example, automatic cancellation when the view disappears. Just to also mention this point that the new Swift concurrency capabilities we're talking about here were included in Swift 5.5 that was announced at WWDC last year. So firstly, let's look at executing async functions sequentially using a slightly adapted version of example from Paul Hudson's excellent series of articles on Swift concurrency. Here we have three async functions: fetch weather history, calculate average temp, and upload, which we're invoking sequentially from process weather, which itself is an async function. Some of these functions would, for example, make a remote API request and have to wait for the response. And this is the Kotlin equivalent. We see here the use of suspend keyword in Kotlin versus async in Swift, again, both denoting a function in which suspension can occur. And also the fact that we explicitly use a wait in Swift, whereas suspend functions can be called directly in the appropriate context in Kotlin. Looking then at some examples how we would invoke async code like this, again, from Paul's examples as a basis, it can be invoked from a main function as shown here, marked again as async in Swift and suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin, create a coroutine from which it can be invoked. Where things get interesting then, I think, is how we can tie this into our UI lifecycle, along importantly then with automatic cancellation when the UI is no longer shown. We use the task view modifier in SwiftUI for this and can use, for example, launched effect in Compose. And we'll see another example of this later. Whereas the previous example showed how we can execute async functions sequentially, Donnie's article about use of Swift's async let and associated examples show how to invoke tasks concurrently. This is, again, a slightly modified version from the sample and shows how we can kick off a number of tasks that run concurrently and wait on them. And we'll see this in a bit more detail in the next slides. And again, this is the Kotlin equivalent. And if we break it down a bit more, we again see use of async in Swift and suspend in Kotlin. Very similar mechanisms then for invoking these async functions in parallel, using async let in Swift and async coroutine builder in Kotlin, and then waiting for them to complete, using a wait in Swift and a wait all in Kotlin. In this case, we're going to load the list of movies and the user info and wait for them to complete. These requests, as I said, will execute in parallel. Finally, we kick up a number of other async tasks that again execute in parallel and again wait for them to complete. The other major component of the Swift concurrency functionality is async sequence that allows asynchronous iteration over a stream of values. And this is something that maps very closely to a Kotlin flow. This is a basic example adapted again from Paul Hudson's articles of use of async sequence in Swift, along then with examples of use of flow in Kotlin. We use for await in Swift to iterate over the values and collect in Kotlin. And then also a few examples of some of the operators supported. Firstly, using map to convert each value to its uppercase version, and again, integrating over the result. And then filter, for example, to filter on a particular string, as I said, in a very similar way. So as I was preparing this section of the talk, and in particular looking at ways in which Swift async sequence operators compare to those supported by Flow, I read a few articles like this talking about aspects of the Swift combined framework that were still missing from async sequence. At the time, there was still a gap that meant that in some cases, developers still needed to rely on combine, or libraries like this async extensions here that mimic some of the functionality it provided. So I was, of course, interested a few days later in seeing Swift async algorithms packaged announced. And with this, we now effectively have even closer mapping between the capabilities of Swift async sequence and Kotlin Flow and the operators they support. And this is a few examples using some of the new operators included in that Swift algorithms package, along with their Kotlin equivalent. Using the new async method provided by that package to convert a Swift array into an async sequence, with asFlow being used in Kotlin to achieve the same purpose. And as before, we use for await in Swift, and we use collect in Kotlin. Showing example first of merge, and then zip here, and several other operators in common now as well. Just to finish this section, I wanted to show one other example where we're now talking about very similar concepts on both platforms, using in many cases the same vocabulary. I watched the session at bottom right at Kotlin Conf in 2019, where Florina and Manuel talked about how cancellation of coroutines needs to be cooperative. And thought it was interesting then to see the structured concurrency talk at WWDC in 21, talking about the same concepts, talking about canceling tasks in the Swift case. Okay, going to talk just very briefly about Kotlin multi-platform, as it's something I think nicely complements some of the developments we've been discussing here, again in the context of developing native applications and in relation to sharing non-UI code. Subtitle here is obviously not the official one, but phrasing like this to perhaps emphasize where this potentially fits in. I heard someone also describe it as writing the code that nobody likes to write. But I should also mention that I gave a version of this talk originally at Swift Heroes in Turin a few months ago, so part of my approach here was to try and make Kotlin multi-platform as least threatening as possible to iOS developers. But bringing it up here as well, we'll see a small example of it in a while. Some of the similarities we're discussing here make the consumption of shared Kotlin code, including async-related code, pretty seamless in Swift. This is a quote from Kevin Gallagher from TouchLab, highlighting again the fundamental difference between cross-platform approaches where we try to share UI, and what I think is a more pragmatic approach where we share some UI logic across the platforms while still developing, very importantly, as native applications. Folks actually might have seen Kevin talking before me, and I should probably mention that he has since updated this quote in recent times, so I hope he doesn't mind me sticking to the original one here, as I think it's more appropriate in this context at least. And a key component of Kotlin multi-platform that's of interest to us here is Kotlin Native. Provides us capability to compile Kotlin code natively using, for example, LLVM on iOS. Typically, a framework is created that can be consumed directly in Xcode. And very importantly, we can access native APIs directly from the shared code if needed. And last point here is something I've been doing in a few examples, which is this nice capability now to build the shared code as a Swift package and add that to the Xcode project like any other library. And just showing here how Kotlin and Swift types are mapped to each other, again, when using Kotlin multi-platform like this. Not going to go through this in detail, but just to give a flavor, and we'll also see some of these in some of the examples we're going through as well. Okay, we're going to finish up with a small example that illustrates, again, some of the areas we've been discussing. This is based on another sample I have in GitHub called Bike Share. That sample illustrates broader functionality But for illustration purposes here, we're going to focus in on showing a list of what are called bike stations for a particular bike network. In this case here, one for the next bike network in Berlin. And this is what the high-level architecture might look like for an application like this. We're building native iOS and Android apps, using Xcode for iOS and Android Studio for Android, using SwiftUI on iOS and Compose on Android, and MVVM on both. We then, in this example, have a shared repository which we're consuming on both platforms. And this is an excerpt from that shared repository that we're going to use in this example. It polls for info for a particular bike network and exposes that as a Kotlin flow, something we'll use directly in our Android client, but will map to an async sequence in our Swift iOS client. And by the way, we're mapping from that flow to an async sequence using the really nice KMP native coroutine library that Kevin also mentioned in the earlier talk, that I definitely strongly recommend anyone working in Kotlin multi-platform to take a look at. It supports new Swift 5.5 concurrency capabilities along with a number of other frameworks. So firstly, this is what a view model might look like for this example. Typically, its purpose is as a container of state, of a container of observable state, rather, changes to which then cause our UI to be re-rendered, and sort of a conduit for actions we're taking from our UI that will typically cause that state to be updated. Also can be used for transforming state which you get from other parts of the code into something more suitable for the UI, though not doing in this basic example. The pattern for iOS is pretty common, I think, using observable object protocol along with published property wrapper. On Android, we're using AAC view model along with Compose's mutable state of. Here, not too important in this context, but common, of course, also to use stateflow here as well as to map to a specific UI state as mentioned. We have this poll network updates async functions, which in the Swift iOS view model that uses the for-await mechanism in Swift, along with that KMP native coroutine library that maps to the Kotlin flow I showed in the previous slide. And it maps that, as I said, to a Swift async sequence. On Android, we're doing something quite similar. In this case, again, using Kotlin flow collect instead of that for-await. We use in Swift, and also triggering when we get new data, update of some state that would cause Compose to re-render appropriate parts of our UI. And this is what some of the SwiftUI and Compose code looks like in this example. Again, we're using a Swift struct for SwiftUI and Kotlin function for Compose, using list in one and lazy column in the other to iterate over the list of stations coming from our view model in both cases. We use the task view modifier in SwiftUI to invoke the poll network updates async function there in our view model and use launch deflecting Compose to effectively do the same thing. And important to note again that this will automatically get canceled when our view disappears. And by the way, that cancellation also gets propagated to the flow in the shared code as well in both cases. Before we show the SwiftUI and Compose code for the rows themselves, just a quick recap on what we're trying to show here. We have a row with tinted image representing how many bikes are available, and then a column containing the name of a station and availability info. This is what the SwiftUI code looks like. A lot to unpack here. We'll show Compose equivalent next and also show trimmed down version, both side by side, to illustrate comparisons. But here we can hopefully see general structure with the image showing the tinted icon, color based on number of free bikes, and then SwiftUI HStack, text elements, etc. This, by the way, is from a sample in GitHub again if people want to look through this in more detail later. This is the Compose equivalent. Again, don't worry about the details too much. As I said, we'll show them side by side in a moment, but much the same structure as SwiftUI version. And this is the pared down version shown side by side. And hopefully, again, we see how the UI elements marry close to each other. HStack to row, VStack to column, image, spacer, and text elements in both, with some API differences and some differences, as mentioned before, in how paddings, styles, etc., are applied. And one final example that illustrates use of combining multiple Swift async sequences. The first one representing a list of players. This one, in fact, mapped to a Kotlin flow using that KMP native coroutines library mentioned earlier. The other then representing a search query, and then using combine latest operator to combine them. And I think this nicely illustrates again how seamless that consumption of Kotlin flow in Swift can be. So that was somewhat of a whirlwind tour of some of the key areas I think had contributed to the increasing convergence of native iOS and Android development. And just to recap, there are, of course, many different permutations in how mobile development teams are organized, depending on the company, the size of the project, etc. But at least now I think we have more possibilities for people working on both platforms and becoming more general mobile developers. We've seen similarities in the language, but even more important and impactful is the common approaches we now have on both platforms for both UI development and concurrency. And complementing that, I think, is the possibility of using Kotlin multi-platform for sharing some of the boring non-UI code on both platforms. Thank you.